Do I have 6 too? No. Okay. I will only show derivation of one and the other is analogous. For 6 to 22 was that dH equals Cp dt plus V molar minus T partial V with respect to T at T dP. So keep that in mind. So pressure dependence of Cp. Take the partial of Cp with respect to pressure at constant temperature. And we know that Cp, what's the definition of Cp? Partial H with respect to T at constant pressure. So that's partial with respect to P at constant temperature of partial H with respect to T at constant pressure. And we can change the order of the partials. So that's partial with respect to temperature at constant pressure of partial H with respect to pressure at constant temperature. And that's why I wrote the expression above. What's partial H with respect to pressure at constant temperature? This bracket. Right? So that is partial with respect to temperature of the bracket above all that at constant pressure. And so that is equal partial V with respect to T at constant pressure. And here I have partial respect to T of this. We can use product rule. So first take this out, partial respect to the second, and then take the second out, partial respect to the first. So let's write it this way, minus T second partial with respect to T at P. Oh, this is at P. Oh, actually, I did write it. So second partial of V with respect to temperature at constant P, and then I have minus the partial respect to T is 1, so minus partial V with respect to T at constant P. Do you see a cancellation? You lose me? Anyone lose? Follow this product rule. So I have the product, I have the derivative of this product. So what I did is first minus T times the derivative of this, and then plus minus the derivative of minus T times this. Okay? Ricardo. All right. This cancels. And you have the expression that I was after, that the partial of Cp with respect to pressure at constant temperature is equal to minus temperature second partial of V with respect to T. And from a practical point of view, partial V with respect to T is what? Is the alpha. There's a thermocompressibility, right? And usually, often alpha is taken as a constant. It would depend somewhat on temperature, and this is the derivative of that with respect to temperature. So it's not a very strong temperature. It's not a very strong temperature. So there is some variation, but you can see from here that it's not going to be very strong because you have the derivative with respect to temperature to something that is already a weak function of temperature. All right. similar, okay, this is equation 6237. And similarly, working with the analogous equation with du, what we do with A, Cp and H is Cv and du. Okay? And Cp has P, Cv has V1. So if we do that, we get the analogous expression that is partial Cv with respect, oops, I made a mistake here. I want dependence of Cp. You use Cp when you deal with temperature and pressure. When do you use Cv? When you deal with temperature and molar volume. So I shouldn't say pressure dependence, other dependence. Forgot about that, sorry. So here, for Cv, I want the volume dependence. So the partial Cv with respect to molar volume at constant temperature is going to be T second partial again with respect to temperature at molar volume, and that is 6 to 36. Okay? So possibly in an exam I could ask you to derive what I did derive. Okay? These are derivations, something is completely analogous. You may find an exam problem question to derive what is completely analogous. All right. Now I'll go to something that I was asked about. I don't remember if it was Juan or not. I think it was Juan. Last lecture, and I told him to wait until this lecture. Probably. I don't know what you call the big question, but I think it's, I guess we'll keep that up here. I will remind you that fundamental state variable equations, and I don't remember the numbers, but I remember, without looking at what they are, dh what changes? It changes that to be minus, sorry, gds changes that to be plus vdp. Then dA changes ds d minus s dt minus p dv, and dg changes the minus p dv to plus v dp of the above minus s dt plus v dv. And we talked that we normally have as equation of state a volumetric equation of state. That's the thing. But there are certain equations of state that if we have them would be great. They're called fundamental equations of state. If I have a fundamental equation of state, from that equation I immediately have everything, all 8 state variables. So the next topic is going to be fundamental equation of state. And I put this up as a reminder because it will become apparent why those will be fundamental equations of state. Okay. If you look at the first expression, I have du, I have ds, dv. If I have an equation of state that has u, s, and v, I have a fundamental equation of state. So there are 4 fundamental equations of state. One would be to have a function of u, s, and v equals 0. The second fundamental equation of state comes from this equation. Here I have dh, ds, dt. The function of h, s, and p equals 0 would be a fundamental equation of state. A function of A, T, and V would be fundamental equation of state. And the last one, G, T, and P. Okay, why are these fundamental equations of state? Why, if we have something of that, we can immediately calculate all 8 state vectors? Here is why. Let's do example with the first one. And I will do it first before answering Juan's question. Suppose I had an expression u equals u as a function of S and B. And then I will do it for the F, which is, I think, what your question was. So simplest case is if this can be expressed as u equals, if I have this, we have explicitly internalization as a function of entropy and more. Why can I get all state vectors? All right. I have S and V, I immediately calculate U, right? So, looking at this, if I have U as a function of S and V, I immediately have temperature and minus pressure. Because temperature is what? Temperature is the partial of U with respect to S at constant V. I have this function, put it in, differentiate it, you're done. You have what temperature is. Pressure. Minus pressure is partial of U with respect to V at constant S. So, you have that expression, put it in, you found pressure. So now I have S, V, U, T, P. How can I get the rest? Very easy. H, so now I have, remember, U, S, V, T, and P. Okay, H is what? U plus PV. I have P, I have V, I have U. Okay, so I have H. What about A? A equals U minus TS. Let's see, do I have S yet? Yeah, I have S, I have T, calculate the T, okay, I have U, right? And finally, G is A, for example, plus PV. You have P, you have V, you have A, you got everything. All right? But I wrote the fundamental equation of state as function equals 0, not U equals U of SV. How do I get those partials? So I need to be able to express partial U with respect to S at V and partial U with respect to V at S to be able to get temperature and pressure. So how can I get temperature and pressure if I don't have this explicit relationship, instead I have this implicit relationship? It's very straightforward. Wasn't that your question? No. No? I thought that was your question. Okay. Was someone else's question? How you calculate that if you don't have U as direct as a function, you have a general function? No? Okay.
So the question has answered.
Ask if you remember, ask me again after class. All right. So I have a function f of U SV that means that since it's a function f of those three quantities, that means that any differential in f is going to be equal to the partial of f with respect to one variable, keeping the other two constants, the u, try to make my u's not look like this, plus the partial of the function with respect the second variable and the other two constants, ds, plus the partial of the function with respect to v keeping s u and s constant dd. Okay? And if I want, what do I want for temperature? For temperature, I need partial u with respect to s at v. I have a given f, right? The f is available at fx. So to get temperature, I'm going to take the partial in this expression with respect to s at constant v. For t, I can write partial f with respect to s at constant v equals partial f with respect to u at constant s and v times partial u with respect to s at constant v, which is what? The temperature I'm looking for, plus partial f with respect to s at constant u and v, partial s with respect to s at constant v, which is of course equal to what? 0, 1, ds. Plus, the next guy is going to be 0, plus partial f with respect to v at constant u s times partial v with respect to s at constant v, and this guy is of course 0. So temperature is going to be equal to it's this minus that over that what I don't. Oh yeah, sorry, mistake. What is f though? Not quite mistake, hypothetical. But what is f? It's constant, it's 0. So the differential of f is going to be 0. The partial f with respect to something is 0. So that's equal to 0.
What about the partial just that? What about the partial just that? Just 0?
No, that's the functionality. F itself,
What is it here?
the differential of f has to be 0. Because f is 0. F itself cannot change. Okay? So that I should have put equals 0. Okay? So temperature equals minus partial f with respect to s at constant u and v divided by partial f with respect to u at constant s. Okay? If I was looking for p, I would do it with respect to v. Yeah, I should have put the equal 0 right away. We can have differential in u, we can have differential in s, we can have differential in v. But because f is equal to 0, the df equals 0. I should not have, probably I shouldn't have put this, because this is 0.